I'm Roselle.
Hi, I'm Alyssa.
Hi, I'm Kenneth.
Hi, I'm Marvic.
And we are the Register Group!
Before we begin, let's first recall what flip-flops are. Flip-flops are 1-bit memory that can store 1 bit of data. Data can either be 0 or 1. To increase data capacity, we have to use a group of flip-flops which is called a register. An n-bit register consists of n number of flip-flops, and it is capable of storing n bits of data. Let us look at 4-digit register. The 4-bit register is made up of 4 flip-flops because we know that D flip-flops can store data. In here, D is the data input and Q is the data output. A clock is then connected to each flip-flop of the register, in which the register is bound to follow the clock frequency. In one clock pulse, data is stored in the register, then in another clock pulse, data is reset on the register. For instance, if we try to input 1, 0, 1, 1 into our 4-bit register, it will be stored in the register after 1 clock. Then, it will be reset after another clock pulse. So, if we have a clock having a frequency of 1 MHz, then it means that 1 clock pulse is equivalent to 1 microsecond. Using a square wave, it means that every falling edge will be made after microsecond. This implies that the data will be stored after 1 microsecond. Then, it will be reset after another 1 microsecond. What can we do to prolong the storage of the data into the register? We use an independent control, which we call a load. The load can be of 2 types: the synchronous load and the asynchronous load. In the synchronous load, the data will be reset when both clock and the load is high. In the asynchronous load, the data will only be reset if the load is high. Using this load, we can prolong the storage of our data by setting the load to low for a certain duration. For instance, if we want to store our data for 100 microseconds, we will just set the load to low for 100 microseconds. After that 100 microseconds, the load will be high again. At that time, the register will be reset. A clear is also connected to each flip-flops so that it will be all in 0 once no data will be inserted into the register. Let us move on to data formats. Data can be entered in serial or in parallel form. By serial form, it means data will be entered 1 bit at a time. By parallel form, it means data will be entered all bits at a time. Let us look at a 4-bit register again. If we enter the data from one side, it will be in a serial manner. Let's say that we will enter a 4-bit data, which is 1011 in a serial manner. If we look at its square wave, it will look something like this. If I then want to enter the data in a parallel manner, then I need to enter each bit individually to all the flip-flops. If we look at its square wave, it will look something like this. If we can input the data in serial form and in parallel form, then we can also extract the data in serial form or parallel form as well. If you want to extract it in serial form, then it will look like this. If you want to extract it in a parallel form, then it will look like this. The serial format can also be called as temporal code, and the parallel format can also be called the special code. Further discussion on data will be made in the discussion of different operations. Let us move on to classification of registers. There are 2 ways in which we can classify registers. One way to classify is depending on the mode of input and output. There are the serial in, serial out or seesaw, the serial in, parallel out or SIPO, SIPO, the parallel in, serial out, or PISO, and the parallel in, parallel out, or PIPO. More of this will be discussed later. Another way to classify is depending on application. The two types under this classification are the shift registers and the storage registers. Shift registers used when data is shifted within the register from one flip-flops to another. Storage registers are used when data is temporarily stored in the register, then extracted but immediately when needed. In the four modes of input and output, one can say that CISO, SIPO, and PISO are shift registers because in these modes of operation, data is being shifted from one flip-flops to another. PIPO is then the storage register because in PIPO, data is stored all bits at a time, then extracted all bits at the same time, also when needed.
The first mode of operation that will be discussed is the serial in, serial out register or the SISO. In this operation, data is entered and extracted both in a serial manner as the name suggests. There are two types of SISO, the shift to the right mode and the shift to the left mode. The difference between these two is that the former enters data from the left and then it is shifted to the right, while the latter enters data from the right and shifts data to the left. In this section, we will only discuss the shift to the right mode. It is also applicable to the shift to the left mode, which is just opposite of the first mode. Let us examine the schematic diagram of the SISO register. As you can see, the clocks are connected to each of the four flip-flops. The D input is where we will enter the data, which is connected to D3. Q3 is the output of flip-flop 3, which is connected to D2, and so on until it reaches Q0, which gives us the serial output. Initially, all the flip-flops are 0. Let's say that we want to input 1101 into the register. To do this, we need to locate the LSB or the least significant bit and the MSB or the most significant bit. In this case, the one on the right is the less significant bit or LSB and the one on the left is the MSB or the most significant bit. The LSB will be the first one to be entered on the register. Once this is made, D3 will become 1 and D2, D1, and D0 will still be 0 since no data has been shifted to them yet. After the first falling edge, the values of the output Q3, Q2, Q1, and Q0 will be the following. After that, the next digit after the LSB will then be entered on the register, while the data on flip-flop 3 will then be shifted to the flip-flop on the right, which is flip-flop 2. Once this is made, D3 will become 0 and D2 will become 1, while D1 and D0 will still be 0 since no data has been shifted to them yet. After the second falling edge, the outputs Q3, Q2, Q1, and Q0 will be the following. This pattern will then be repeated until all the flip-flops are filled with data or the MSB has been entered on the register. Notice that for a 4-bit register, 4 falling edges or 4 clock pulses are needed to store the data. For the square wave of the outputs, we will refer to the table that we have filled up a while ago. Denote the necessary lines, whether the data is high or low in a square wave. Then let's observe the data entered for each clock pulse. Can you observe a pattern in the table? One disadvantage of the SISO register is that if it requires 4 clock pulses for us to enter 4 bits of data, it also then requires 4 clock pulses for us to extract 4 bits of data. That is where the serial in, parallel out, or SIPO register comes in. The The schematic diagram for the C4 register is like that of the CISO register, but instead of connecting Q3 to D2 and Q2 to D1 and so on, Q3, Q2, Q1, and Q0 will be outputs on their own. This means that in this mode of operation, data is entered in a serial manner and extracted in a parallel manner. So instead of having one output on the right, 4 outputs are then used. And instead of requiring more clock pulses like in CISO, at least one clock pulse is required to extract all data bits in CISO. Let us now move on to the parallel in, parallel out, or PIPO register. As said earlier, PIPO register is also called as the storage register, since it is only used for data storage and data is not shifted on the adjacent flip-flops. Let us examine the schematic diagram for PIPO register. In here, all bits of data are entered in each flip-flop after each falling edge. For an instance, we are to enter 1011 in the register. Looking at the square wave, we will make D3 high, D2 low, D1 high, and D0 high before the first falling edge. After the first falling edge has arrived, data in D will also be the value in Q. In turn, this makes Q3 high, Q2 low, Q1 high, and Q0 high after the first falling edge. This then will make the extraction of data in a parallel manner. Now, let's say that we will enter a new set of data which is 1000. After one clock pulse or one falling edge, the data 1011 will be extracted from the register and the data 1000 will be entered on the register.
Lastly, let us go on to parallel in, serial out, or PISO register. As the name suggests, the bits are entered in parallel then extracted in series. Let us see the schematic diagram of this type of register. The important thing to know here is that the output of one flip-flop is connected to the input of one flip-flop adjacent through a combinational circuit. As you can see, the combinational circuit used here is composed of 2 AND gates and 1 OR gate. Here, 2 models are used for the combinational circuits to work. One, the load mode, and the other one, the shift mode. In this register, we have 2 aims, which is the parallel input and the serial output. The first aim will be achieved through the load mode. This is the mode where the data will be entered in parallel. Input B0 will be in flip-flop 0, B1 in flip-flop 1, and so on. Let us examine how this load mode works. For this, you need the input of shift/load complement, and the load is in complement because during input, the load should be low. So when the input here is low, the input here will be high, while the other will be low. This will be the inputs of the different AND gates that we will use. Looking at the diagram, the first inputs of AND gate numbers 1, 3, and 5 is 0, while the first inputs of AND gate numbers 2, 4, and 6 is 1. The other inputs for AND gate numbers 1, 3, and 5 will be the values of Q0, Q1, and Q2 respectively. This will make the outputs of AND gate numbers 1, 3, and 5 to be 0. The other inputs for AND gate numbers 2, 4, and 6 will be the values of B1, B2, and B3 respectively. This will make the outputs of AND gate numbers 2, 4, and 6 to be the values of B1, B2, and B3 respectively. Lastly, this will make the outputs of OR gate the numbers 1, 2, and 3 to be the values of B1, B2, and B3 respectively. This results in flip-flops 1, 2, and 3 to have a data value of B1, B2, and B3 respectively. As we can see, the data values of B0, B1, B2, and B3 will be the data stored in flip-flops 0, 1, 2, and 3. Now that we have entered the data during the load mode in a parallel manner, it's time to shift the data in each flip-flop during the shift mode. During the shift mode, the data input for the shift/load complement will be turned to high. Because of this, we will have a high here and a low here. This will now be the different inputs for the AND gates in the combinational circuit. The first inputs of AND gate numbers 1, 3, and 5 will now be 1, while the first inputs of AND gate numbers 2, 4, and 6 will now be 0. The other inputs for AND gate numbers 1, 3, and 5 will be the values of Q0, Q1, and Q2 respectively. This will make the outputs of AND gate numbers 1, 3, and 5 to be the values of Q0, Q1, and Q2 respectively. The other inputs for AND gate numbers 2, 4, and 6 will still be the values of B1, B2, and B3 respectively. This will make the outputs of AND gate numbers 2, 4, and 6 to be 0. Lastly, this will make the outputs of OR gate numbers 1, 2, and 3 to be the values of Q0, Q1, and Q2 respectively. Now, let's have an illustrative example in how this is done. Let's say that we will enter 1, 0, 1, 1 in the PIPO register. The values of B0, B1, B2, and B3 will be 1, 0, 1, 1 respectively. During the load mode, 1, 0, 1, 1 will be the data stored in flip-flop numbers 0, 1, 2, and 3 respectively. Then, during the shift mode, the data will all be shifted to the right. The shifting of the data will continue until all the data bits have been shifted out.
Before we go on to the bidirectional shift register, let us look at the 2-bit data, which is 1, 1. The decimal equivalent of 1, 1 is 3. If we shift that to the left, then we get 1, 1, 0. The decimal equivalent of 1, 1, 0 is 6. This gives the idea that shifting data to the left multiplies its decimal equivalent by 2, while shifting data to the right divides its decimal equivalent by 2. If you want to multiply or divide your data by 2, then this is where the bidirectional shift register is needed. Bidirectional shift register, as the name suggests, is a shift register that can shift data either to the right or to the left, depending on what the user needs. Let us now look at the schematic diagram of the bidirectional shift register. Like previous ones, we use a 4-bit register with flip-flop numbers 3, 2, 1, and 0. A combinational circuit consisting of 2 AND gates and 1 OR gate is used here, like in the PISO register. A mode control input is also used here, denoted by M. The direction of the shifting of data is determined by the value of M. If M is 1, data is shifted to the right, while if M is 0, data is shifted to the left. Let's now look what will happen if M is equal to 1. We will have a value of 1 here and a value of 0 here. In this condition, the initial inputs of AND gate numbers 2, 4, 6, and 8 is 0. This disables the mentioned AND gates, which gives an output of 0. The initial inputs of AND gate numbers 1, 3, 5, and 7 is 1. This makes the other inputs of the mentioned AND gates to be the values of DR, Q3, Q2, and Q1 respectively. This makes the outputs of the OR gates 1, 2, 3, and 4 to be the values of DR, Q3, Q2, and Q1 respectively. This is how data is shifted to the right. Let's now look at what happens when M is 0. We will have a value of 0 here and a value of 1 here. In this condition, the initial outputs of AND gate numbers 1, 3, 5, and 7 is 0. This disables the mentioned AND gates, which gives an output of 0. The initial inputs of AND gate numbers 2, 4, 6, and 8 is 1. This makes the other inputs of the mentioned AND gates to be the values of DL, Q0, Q1, and Q2 respectively. This is how data is shifted to the left. Thank you for watching!